Good afternoon, professors. We are the team from BIMCSS, and I'm Choi Yang. Today we are presenting on the 3D solver problem, which is originated from the 2D moving solver problem. And the 2D moving solver problem aims to find the largest area of the shape that can pass through the L-shaped corridor. And our project aims to extend the 2D problem to 3D and involve more practical applications. And we want to find the largest volume of the prism that can pass through the staircase. And also we want to and then we only investigate the prism because it's similar to the shape of the real-life sofa. And then we parameterize the lines for constructing the staircase, which we denote it by h. And then we have 4 parameters here: w, h, theta, and phi. And then our staircase is constructed by 2 hallways connected by a platform region, which the platform region is in the shape of the sector to simplify further calculation. And then there are 2 main properties of the staircase. The first one is the definition of h1 and h2 can be swapped, and it's identical to pass through the staircase from both sides of the hallways. And this means that the hallways are symmetric. And we prove this by first the reversible path of the object, and also by constructing a rotational matrix of the hallways. And then the next property is the convexity of the object size constraint. We denote alpha as the rotational angle of the object. And then we prove that the tightest constraint is at the middle angle, which is alpha equal to pi minus theta over 2. And we first denote M as the largest volume of the convex object that can pass through the staircase, and the M must lies in between this pink plane and the walls of H. And the space in between is denoted by T, and then we find the expression of T, and we prove that T is minimized at the middle angle. And for rectangular object, M is decreases with T, therefore M also minimized at the middle angle. So we only need to consider the tightest constraint at the middle angle for further calculation. And then let's move on to our main results. We first assume that the hallways is infinite length, and we first investigate the 1D line length constraint. And we prove that the longest line, it must touch the corner of H. And then we find the length expressions of the 1D line, and then we prove that the length constraint is at the middle angle also. This also supports the previous convexity of the object constraint. And then for 2D rectangles, we construct it in 2 ways to simplify the calculation. And for case 1 rectangle, we construct it by widening a section of the L maximum on the xy direction until its corner touch the wall of H. And then for case 2 rectangle, we construct it by the projection of the L maximum onto the wall, onto the floor and the ceiling of the H. And then we connect them by lines perpendicular to them. And for case 1 rectangle, we construct, we first denote x as the width of the rectangle, and then we consider projection of the rectangle onto the xy plane. And we need to consider whether the rectangle touch the platform region or not. Therefore, we get 2 ranges here, and the critical value is here. And we find the 2 expression of the area. And then by differentiating them, we prove that the 2 area are maximized as these 2 x optimized. And for different parameters, the area is large. Both expressions may have a larger value. Therefore, we take the S1 optimized as the larger one of these 2 expressions at the middle angle. And for case 2 rectangle, we first denote tau as the vertical distance between the floor and the point that the rectangle touched the H1. And then by differentiating the S2 with respect to tau, and then we may find the S2 optimized. And for the total A maximum, which is the area constraint, is the larger one of the 2 optimized expressions. And then for 3D cuboid, we construct it similarly to the 2D rectangle. Like we extend the 2D case 2 rectangle on the orthogonal direction, like here. And then we first denote the width as A, and the length L and height H can also be expressed in A2. And by geometry, we find the H expressions. And for the length expressions, we consider the projection of the base rectangle onto the xy plane. And then similar to the 2D case 1 rectangle, we need to consider whether the rectangle touched the platform region or not, and therefore we get the critical value of it, which is the AC, and then we find the expressions of the length in 2 parts, and then we differentiate them, and then we differentiate them with respect to A, and then we find that in the range 1, the V is either maximized at A optimized or at AC. And V maximized at the AC also means that the total V maximum is in the second range. And in the second range, we find the V, differentiate them, and finally find this polynomial equation. And we solve it by the Python program. And the Python program also gives us the expression, optimized expression in these two ranges. And therefore, the total V maximum is the larger one of these two expressions. And then let's move on to the finite hallways. We first generalize the length of L1 and L2, which is the length of H1 and H2. And without loss of generality, we may assume that L1 is smaller than L2 because the hallways are symmetric, that we can swap them. And at here, the longest line touch the H1 at lambda 2. And then for L1 longer than lambda 2, the object constraint is still at the middle angle, which is alpha equal to pi minus theta over 2, and therefore is exactly the same as the infinite case. Therefore, we don't need to consider this case. And for L1 smaller than lambda 1, that there are infinite lines that can pass through a staircase without any rotation. Therefore, we only need to consider L1 between lambda 1 and lambda 2. And in this case, we can see that there are also an infinite line that can pass through the staircase. And by considering the angle at the corner of H, we may find the critical value of L1 and L2 here. And based on this, we then prove that for L1 between lambda 1 and lambda 2, and if there are no infinite line that can pass through a staircase, we prove that the object size constraint is independent of L2. Therefore, we only need to consider L1 for further calculation. And then at the beginning of the movement, we place the object at the edge of the H1, and then we define the initial alpha as the arctangent W over L1 cosine phi. And then because of the convexity of the hallways, like the object size constraint, the length constraint of the line is still at the initial alpha. Therefore, we can sub the new alpha into the original expressions, and then we can find the new length expressions. And for 2D rectangle, because the hallways is no longer symmetric, therefore for case 1 rectangle, there are 3 ranges now. And then we prove that there are no extreme point in the middle angle, in the middle range, and therefore the S1 optimized is substituting the new alpha into the original 2 ranges expressions. And the S2 rectangle is not affected by the non-symmetric situation, therefore the total A maximum is substituting the new alpha into the original maximum expressions. And then for 3D cuboid, similar to the 2D case, there are 3 ranges now, and we need to examine them. And we deal with it, like we solve it by the Python program again, and we finally sub the new alpha into the maximum expressions. And we conclude our main result by this Python program, like we may measure the dimensions of the solver, and also the parameters of the staircase, which is W, H, theta, and phi. And then we may determine whether the solver can pass through the staircase or not, and also the code can also give us the maximum volume of the prism that can pass through the staircase. And besides our main results, we also investigate the longest arc that can pass through the staircase, and this provides more direction for further calculation. And also our project aims to extend the abstract geometry to the real-life application, that we mainly solve it by calculus and algebra. And we believe that our project is quite useful for real-life, like home solver transformation problem. And for further exploration, people may also examine the largest size of the shape, like for example spheres that can pass through the staircase. And thank you for your listening.